Welcome everyone to the sixth Power Grid Model Meetup. Looking at all of you, I have to think about the first meetup that we had a couple of years ago, where we all fit in one small meeting room at Alliander. Well, that's no longer possible. Also, a lot of people joining online, and this is also our first full day event. So we're really curious how it's going to be. We're really excited for it. Before we start, I would like the Delft University of Technology for hosting the day. And I would like to inform you that the session is being recorded and photographed. Just so you know. First things first, some safety things that I have to mention. In case of emergency, follow the signs of the emergency exit. So for people here, that's either that door or the door in the back. Don't drive and call. Also not hands-free. It says here as well, indeed, that the session is recorded and photographed. For the people online, you can post your questions in the chat. And for the people here, we have a catch box. So most of you might be familiar with it. But if you have a question, we'll throw you the box. And please hold it really close. Else it doesn't work. Also, for the people that came by car, we have a QR code. It's over here, so you can scan the QR code with your phone, and then at the end of the day, you can drive out for free. So let me introduce myself first. My name is Peter Salemink. I'm the chair of the Power Grid Model project. I'm a scientific software engineer and team lead at Alliander. And I'm also a guest lecturer at Eindhoven University of Technology. And today I'll be the host of the event. We have a lot of interesting sessions and a lot of presenters as well in the afternoon. But I'll be your host throughout the day. Let me tell you something about the project governance of the Power Grid Model project first. We have a technical steering committee. So it consists of me, Werner van Westering, Tony Xiang, who's in the room, and Jonas van de Boogaard. So we steer the Power Grid Model project. And then we have a group of maintainers. So we have Nitish Barambe, Jen Wang in the back, Martijn Govers here, Jerry Guo with the camera, Santiago, and Laurie Nas, also in the back. And since this year, we have a new project, Power Grid Model DS, which also means we have 4 new maintainers for our Power Grid Model. That's Thijs Baayen, Jaap Schouten, Vincent Koppe, and Sven van der Voort. And then, of course, we have a lot of developers and contributors from outside that are not the maintainers. Some of them will give an interesting talk today about some contributions they've done to the project. So let me tell you a bit about how our development cycle works. So it's community driven. We start here today at the meetup with you. So it's an inspiring event, but we also want some feedback from you that we can use to make the roadmap for the coming year. And then, we'll do some development throughout the year. We'll have community feedback. And then in a year from now, we have our meetup again and see where we stand. And then we do the same round again. So talking about the roadmap, for the people in the room, we have this board. If you have any new feature requests or anything you would like to let us know, please put it on the board. You can do it throughout the entire day. And at the end of the day, we'll collect all of your ideas so we can include it for the roadmap for the coming year. For the people online, you can post your ideas in the chat. So let's have a look at the agenda. We're almost done with the introduction. After that, we have some breakout sessions. So in this room, we have a Power Grid Model DS workshop. And in the other room, we'll organize a hackathon on how to contribute to Power Grid Model. So together with some maintainers, you'll pick a topic and try to contribute something to the project. At 11:45, we'll go out for lunch. It's in a different building, so please follow us. But we'll guide you in the right direction. And then at 1, we start with the afternoon session. So we have 3 interesting presentations. We have 3 lightning talks as well, so that's something new, really short presentations. The maintainers will show you the project highlights. And then at the end, we have a closing. And for the people physically attending, we have some drinks as well to get to know each other better. So this is the afternoon. First of all, so for the morning session, we start with the Power Grid Model DS workshop. So that's the Power Grid Model Data Science project, our new project from this year. You'll be introduced to the Power Grid Model Data Science framework. You'll get a hands-on experience with real use cases, modeling and simulation walkthroughs, integration with data science tools, and interactive Q&A session and discussion. So if you're interested in that, stay in this room. Also for the people online, really easy, stay in this Teams call. And for the people that are interested in joining the hackathon, we have 4 different topics that we can provide today. The first of all is improving code quality by resolving Sonar Cloud warnings. You can follow Martijn. The second one is creating an IEEE validation test case, for which you can follow Nitish. The next one is to modify attributes in the C++ core of Power Grid Model. You can follow Jerry for that. And the last one is to improve the Python API with attribute enums. And you can follow Santiago for that. So, well, you can follow either of them because they're all in the same room. But once you're in the room, you can follow the right person to work on the right project. For the people online, we'll put a link in the chat. That will be done right now. So you can join that link, and from there you can split into the breakout rooms for the hackathon session that you want to attend. Then there's one slide that we just added that I would like to put on the screen for a minute or so you can make a picture of it for everyone attending here. Because for Wi-Fi, you can follow the steps that are on screen, and then you get Wi-Fi access for the day. So you can well, actively participate in one of the 2 sessions. So that's it. That's the opening for the morning session. So if you want to perform in the hackathon, please follow one of the maintainers to the other room. And if you're interested in the Power Grid Model Data Science workshop, please stay in this one. All right.
Okay, nice to see everybody who's staying for the workshop today. As Peter already mentioned, we have launched a new project within the Power Grid Model organization, which we have been developing within Alliander for quite some years now, working on data science solutions, so actually using the Power Grid Model calculation core, and we have experienced a lot of features we developed were quite handy to do that in all settings we are developing internally. So we worked on making that available as well to the community. So that's really exciting. We have been able to do that past year and are able to share that today as well. And we'll be also talking a little bit more about how that came to be in the afternoon in one of the lightning talks, and have prepared 2 workshops for you in the morning. So I'll be introducing a little bit about that now, and then we'll leave it to you to follow the workshops from our repository within a Power Grid model. So I'll give you some instructions later on, and then Thijs, Sven, and I are here to help, and we'll go to the solutions throughout the workshop as well. So maybe a really brief introduction, and then we'll mainly focus on the exercises we have prepared. But what the Power Grid Model Data Science Toolkit brings is an interface which is more aimed at using load flow core from the Power Grid model within a data science setting where we want to answer questions about output from calculations we do. So that means we developed more object-oriented grid approach around the core calculation of the Power Grid model, which allows us to analyze results more easily, modify the grid, and in that way answer questions which we actually are seeing in the real world. And that's also what you will be doing in the workshop. So I think that's really exciting, and hope you'll enjoy it. So I'm going to give a really short overview of what the grid object contains, and that revolves around two representations of the grid we need to be able to simulate, for example, changes in the network, and that is that we want, on the one hand, to have array representation, which we use to input into the calculation core, but also to analyze results. And on the other hand, we have the grid represented as a graph structure in which we can analyze and modify the structure, which combined allows us to answer a lot of questions regarding the network we are analyzing. So that means we are extending, on the one hand, NumPy, and on the other hand, we're using the Wurstwerk X framework for high-performance graph analysis. So we split the workshop into two parts. We have an introductionary workshop, which is really more aimed at getting you familiar with the Power Grid Model DS interface and the structure I showed you before. This will be a little bit shorter. We'll start with that. And then we'll have a more advanced real-world case in which we are going to solve, or everybody of you is going to solve, a contingency within the network. And I hope we'll all come up with some creative solutions for that. And both workshops will be split in a part where you'll be able to try to solve it yourself. And then we'll go through the solutions with you together. So let's see, do I have one more? Yeah, I think that's the point where we're going to start with getting you set up. So everybody has to already get a little bit of an instruction if you got the mail beforehand, but it's quite easy. So you can go to the Power Grid Model Workshop repository. It also contains extended introduction about how to set up an environment in the README, but we also put some brief instructions in here. And it contains two notebooks, the introduction and the advanced one, and we'll start with the introduction one. So let's see if you can get that set up and ask questions if you need any help. And the structure of the workshop is such that every exercise builds on the previous one, and to make sure you can do all the exercises, even if you don't solve one of the puzzles, you can load solutions which are also provided in the repository. So each cell with the load solution comment, if you uncomment the load solution and run the cell, it loads the solution we've developed previously, and you can compare your own or see how you would have solved it. So let's see if that works. It's our first workshop, so I hope we'll manage and you enjoy, and feel free to ask questions to us. So let's see if we can get started.
zo maar wat setup en dan even checken. Ja,
Yep.
ik zou...
I don't think I will be using this a lot more, so I'll put it away. Yeah, I can do this. So maybe if there are people online, of course you can also follow the workshop, but it will be much more difficult for us to give assistance. But the workshop should be self-explanatory and the solutions are included. So I hope you will also enjoy and can be able to join the plenary reviews of the solution as well. So.
Okay. I hope everybody got set up and maybe got through the workshop already, the first introductory workshop. We'll now go through it together. And so we can see how it all worked. So the introductory workshop is about discovering what features are in the Power Grid Model DS project. And I'll just go through the cells. So first we'll import the necessary modules. And in our first exercise, we want to add extra information to the node and line array. So we're actually extending node and line arrays that are as they are defined in the Power Grid Model calculation core, and we want to add some extra attributes to them. So this was not clear for everybody, but if you uncomment this line and you run the cell, you get the solution. And yeah, as you could find in the documentation that was mentioned in the hint, to define your own array, you just subclass the node array from the Power Grid model, and you can add extra attributes like this, and then specify defaults and specify the types using this. Another option is to specify an integer or specify a string, but in this case we work with floats. So I hope that that worked for everybody. Did everybody manage to do this? Great. Then we'll go to the next one. So we now have two custom arrays defined, and the Power Grid Model DS project has a default grid that contains all the arrays. But if you extend an array, you want to update that grid as well so that it contains your extended arrays. So that's what we do in the next assignment. It's a bit windy, the microphone. And it's pretty easy, pretty straightforward. So you just subclass again the grid provided by the Power Grid Model DS project. We call it extended grid in this case, and then we redefine the node and line array in this case. So that was, in my view, straightforward as well. Next step. So now we have a class, the grid class, and then we actually want to instantiate that grid class to an instance, and that's this. So then we have there's an empty class method on the grid class, and it creates like just a grid with all arrays in the grid being empty. Not sure how this. You can print, I think, or maybe it's in the next one, right? Yeah, in the next one you can print the properties or all the content of that grid. So we'll skip to the next one. Right. Or in this case, we're printing the node attributes and the node array by itself and the line attributes I from. Oh, I think I missed a step. Grid is not defined. I should run this probably. Ooh, what's going on, guys?
I think you didn't run all, but they only loaded.
Aha.
Run all cells as well. You can do.
I'm a bit of a notebook noob. I work with Python files. Okay, great, thanks. So now we have and here we can actually see the output from the empty instantiated grid. So yeah, it's just a long list of empty things, but you can see already have a sneak preview that there are a lot of extra arrays in here that are just inherited from the original grid class, but they're all empty. And also our node array, if we zoom in on that, it's still empty because there's no records underneath here. And then we're going to add some data to our grid. So first we add a substation node, or needless, a node that represents a substation. And we do it like this. So we specify the data for each attribute. In this case, we want to add one node, so that should be specified as a sequence or a list in this case. You can also put in an array. It works both ways. So we have one record with ID 101. This is the U-rated value, and then it is a node type substation as an enumeration. And we can append it to the grid, and by appending it to the grid, it will be added to the node array. Just a pro tip: if what we do, or you can also do, is not provide any ID, then it will. If you then instantiate your node array without an ID, it will get an empty value, a predefined empty value. And if you then append it, it will automatically add an ID. This function will then add an ID to the grid. It's very important for the grid to have unique IDs across all arrays, but the append method will make sure that will be the case. So now we have added the node array, the substation node, and we can print. Oh, I think I forgot running this again. Yes, so now we have the node added to the grid. Did everyone get so far as this as well? Or is it, okay, are you able to follow? If not, tell me. And we add a second node, so it's basically the same, but just this is just a regular node. So one more, but in this case the node type is unspecified. So I'll try not to forget to run this time, and then we actually have two nodes now in the grid. We can ignore these attributes for now, but they will be used in the advanced notebook after this. And then the next kind of asset we can add to the grid, which is a line. Very similar. We just have to define a bit more attributes. So, but in general, it works the same way. So you can also append it, specify ID, and specify the attributes. And you have to. Now we have two nodes, and we want to connect those nodes with a line. So you have to specify a from node and a to node. I think actually the framework will also raise an error if you specify an existing node here. So it will do some validation for you in that sense. And these two attributes mark whether the line is an active connection, like there's power flowing through, or whether there's no active connection, the switch is turned off. And they need to be both set to 1 to be active. And once we run this, we'll print it to verify it's been added, and you can see the line array has a bit more attributes. And then we want to add some load to the node. So this is a sim load array. It's also specified by the input data model for the power grid model calculation core. So we're basically copying that. This is just a basic sim load array, so we did not extend it with any custom attributes. But of course, if you want, you can extend the sim load array as well. It's pretty flexible in that sense. So here we refer to a node. It has its own unique ID. It's a specific type, and then we can add some extra attributes here. Append and validate or verify that it's there. So it's all going smoothly so far. And we need to add a source. So a source, I think, defines a starting point for the power to flow from. I'm not an expert on electrical theoretical knowledge, so maybe you guys can correct me, but this is how I understand it. And for the power flow to work, you need to specify a source node as well. So this is, well, again, similar, how you append a source, and then it's there as well. And we want to check, like I mentioned, it's important that all IDs are unique. So with this function, you can check whether that's the case. In this case, it doesn't fail, so there's no error. Then it should be fine. And in the end, we can print the IDs of all the nodes that we added, all the assets, and that's how it goes. That looks good. And finally, we can visualize, this is working, visualize the thing. We didn't specify any coordinates for the nodes, so that's why they're all on top of each other. They all have coordinate 0, I think. But it's an interactive thing, so you can kind of drag them around, and then you see it's pretty zoomed in as well. So if this is scrollable to the left, oh. So you can also run this, if you run it from the terminal, you can also run it if you full screen, then it works a bit better. In a notebook, it's a bit different. But the square, or the diamond, I would say, purple diamond, it represents this, the substation nodes. And the circle ones, the yellow circle ones, these are the regular nodes. And then this is the line. And if you click on a line or an asset, it will show you the information on that asset. So that's our basic mini grid that we created now. And I think that was the introductory notebook. That was it. Any questions, or was it easy to follow? This was the start. Great. Then we'll move on to the next part, I think.
So for the next exercise, we're actually going to have some fun with a real network. So we're going to analyze a network we have created for you. It's, of course, still a little bit of a dummy network, but it will suffice to show you how Power Grid Model DS works. And you'll go through analyzing where the overloads in this network are, and actually try to solve them by adding a substation to the network and connecting the overloaded parts of the network to that. And that's really similar to what we do in a lot of use cases, simulating the future network or a network with new customers, for example, at Alliander. So I think it's really nice introduction to how it for us helps to model things like this. So it's a little bit more advanced notebook, so it'll give you a little bit more time, but I think it's also interesting to go through it together in the end. And let's see if we can actually solve this puzzle.
So this one will be called the advanced.
Okay, hello everyone. I want to discuss the solutions or the way we did things for the advanced workshop. So I'll go through it step by step, but before I start, are there any questions in general about the assignment? Okay, let's get started. So maybe you read the introduction text, but it said, yeah, we have a congestion currently in our distribution grid, and we want to optimize, automatically determine how to relieve this congestion in our grid. And we do this using the Power Grid Data Science Toolkit. So let's get started. We first import the libraries that we need. And then we start again by extending the data model. So as you can see, this is how the library is set up, right? It provides a baseline for the functionality that you might need, but I think for most use cases, you actually want to extend it to fit your use case. So our use case requires geographical coordinates of the nodes because we want to optimize the distance that our new cable will cover, but that will come later. What more do we need? We need an I from, so that's the current that's actually flowing through this cable one way or the other, and it's determined by the load flow done using Power Grid model. And then finally, we have an overloaded status property. This determines if the node is overloaded or not. And this is, again, based on the current, and then we compare this to the normal current. Okay, this was all given. What is also given is an example grid. So we run this, we load the data. If you're interested, you can definitely check out the load dummy grid function. This uses pandas and just some for loops to append the components from a CSV file, so from raw data, into a Power Grid DS object. That's not relevant for now. This is our grid. So we can see a central substation 101 with 4 feeders. So the feeders are the yellow lines. And there's a difference between the yellow lines and the white dotted lines. The white dotted lines are actually cables that are present, but they are inactive currently. At Aliander, but at other DSOs as well, we operate the grid radially. So that means that the current only has one path to flow from the substation to a node. And only in case of a cable failure, we can actually activate these inactive lines to restore power. If you have questions about that, let me know. For now, we can see that we have a geographically distributed grid with 4 feeders. So as we already said, one of these or some of these feeders are overloaded. So some components in the grid exceed their maximum rating, given the load that we inputted earlier from the CSV file. So what we want to do is actually detect this overload. Now, to do that, we have to do a load flow calculation. Again, for this, we use the Power Grid model backend. I will load the solution right now. So this method says check for capacity issues. It's rather simple. We have some boilerplate code to interact with the Power Grid model, do a power flow, and then important, we update the grid. So it means that we take all the values generated by Power Grid model and actually store them in our Power Grid model DS object. Then finally, we return which lines, so which cables in our grid are overloaded. Now we can see that 4 cables from all the cables that we had in the images now are overloaded. And let's see, the IDs don't matter that much, but the from node and to node indicate where the cable is. So 2 lines from our substation node 101 are actually overloaded. And we can visualize that using the PGM-DS visualizer. And now we can see actually, oh, we have a problem in our grid, right? So the red cables exceed their maximum rated capacity. And this is an issue that we want to solve. So there's, of course, multiple ways to solve this. We can upgrade the capacity of our cable by putting a new cable into the ground. But another way to do this is to place a new substation. So we currently have 1 substation in the center of our grid. And we can place a new substation, connect some of the nodes using a new cable to our new substation, and then supply the required power, the required load, partly through that new substation. And that should relieve our currently overloaded cables. It is, and this is what we're going to do. But we want to do it data-driven. Okay, so first we build a new substation. How do we build that? Well, we just generate an object and we run this code. So this should not be a surprise for you. It's the code from the introduction workshop. Don't forget to add a source array to your substation because otherwise there will be no load flow. And then we run it again, I think. Yes, and now we can, if we add this code, I think, let's see. Oh. Okay, we can see that we have added the substation node to our grid. Currently, it's not connected yet, but it does have a location. Okay, then the next step is to connect the new substation. But so far, are there any questions? Does it make sense? Okay, that's good. Let's see. So now we want to decide how to connect the substation. And we have multiple options, right? Because there's an unlimited amount of cables that we can actually place between the new substation and the overloaded nodes. However, we want to choose the most optimal node to reduce costs. So how do we determine that? We have made a step-by-step plan for you. So first we have to determine which routes are actually congested. So a route or a feeder, it's a bit of the same concept. No. This method first calls grid set feeder IDs. I don't think we talked about this yet. It's a method that analyzes which feeder is used to connect this all the nodes to the substation. So you can imagine if we go up. Oh. Yeah, this doesn't work anymore. Let's go here. All of these nodes, they have one particular branch that feeds all the power from the substation to this node. So for example, node 11 is on this route that goes all the way here to the substation. And all the nodes and all the cables on this route have the same feeder ID. Looking at Thijs and Jaap, that's the way to do it, right? Yes. So we can filter, once we set the feeder ID, we can filter all the components in this route. And the same holds for the other routes, right? So let's see, if we only want to talk about these components that are connected on this route, we can call set feeder IDs and then filter. Okay. Let's see how that works in code. Okay, so we call set feeder IDs, then PGM-DS does some work in the background to set the IDs. Then we want to filter, or we ask to our previous method which lines are congested, so which lines are red. And then of those lines, we check what are their feeder branch IDs. So basically, on what route are they? And then we end up with with all the routes that have one or more congestions in them. Okay, maybe we can also. Look, now we have some data. So we can see that there's 2 routes that currently have congestions on them. This also matches our image, right? We had 4 lines that were overloaded, but these 4 lines were part of 2 routes. The other 2 routes starting from the substation had no congestions. Okay, questions about this? Yeah. That's a good suggestion. Let's see. Okay, yeah. So previously, and you can still see this actually for the substation nodes, it had like a large number. This is the default number that we use within the library, but the other nodes actually have a set branch feeder branch ID and feeder node ID. So these refer to the first branch and the first node on this route. And you can uniquely identify each component on the route according to these properties. Yeah. Yeah, if you no ever, so your question is, if you no longer have a radially operated grid, what happens to these IDs, Vincent?
It picks one at random. Like it sees that there are 2 feeders in that route, and then it picks one at random. And you can either detect it by looking, are there 2 feeders with the same feeder branch ID? Then it's meshed, or detect cycles, which is also provided by Power Grid Model DES. So there's a cycles function which you can call to see which routes are cycles.
Would it be nice to use the distance and take the feeder ID from the feeder which is the closest in comparison to simply picking a random feeder?
Okay.
No, it is still connected to both sides, but you pick the feeder ID just for your information in this array, the one which is closest.
So,
because as if I understood correctly, the idea now or the implementation now simply takes some random.
yeah, so random in the sense that we pick the same one for every node and branch in that route. So if you can go up, maybe, then, so if you have a route that's a cycle, then there are 2 feeders in there, and every node and every line in that route will get the same feeder branch ID and the same feeder node ID, but it will be one of the 2. Like there's no real answer. So the main purpose is you can still filter out that route with the feeder branch ID. That still works. But another property is that the feeder branch ID also points, like, is the actual ID of the line that departs from the substation. And that might not be as relevant if there's a cycle anymore, but that's up to the user to like check for. And
Configurable parameter would be an option. So the user can decide which feeder ID.
Maybe we can write it down and discuss it later.
yeah.
Yeah. I'll trust Vincent to write this down after the workshop. Yeah. Okay. Thank you. I think this is a very relevant discussion. Let's see. So, like Vincent said, we can still uniquely identify each component on the route by the feeder and branch ID. And then I want to go back to the task at hand, because of all these routes, we want to see which routes are congested, and then one by one provide a relief strategy for them by connecting them to the new substation. So now we do have a route, which is the input to our next method. And we also want to input the new substation as input to our method. And then the task is to find where to connect the new substation. So basically where to generate or where to build a new cable. Let's see. So we do this according to geographical distance. So I think we're all familiar with Pythagoras. We calculate for each node on the route what is the distance from the new substation to this particular node on the route. We actually do this with a one-liner, right? We don't have a for loop here because these route objects or this route object is actually an array, a NumPy array, and we can use NumPy methods on this. So we subtract actually an array from an array, then we do some squaring and some square roots, and by picking argmin, we select the node that is closest to our new substation, and we return that. Any questions on this? Okay. So finally, we want to create a new line from the node that we have just selected. And then it's important that we first create it with an open connection because we want to maintain a radial grid. So how do we do this? So this method creates a new line array. So like we did before in the introduction workshop, you have to give a bunch of parameters. The from node is the new substation ID, and then the to node is the connection point ID. So this we have determined earlier. The from status is set to 0, so this means it's an inactive line. We can see that in the visualization by the white dotted lines. We give an normalized current and some other physical properties of the line. And now it's time to actually do the optimization, or we did some optimization before, right? By determining which node we want to create the cable to. And now we want to wrap it up. So this is a pretty big function. I'll load it first and then go through it step by step. Okay. We want to optimize which cable to open because we have created the line now. We want to close it. We want to connect the node to the new substation, but then we have to open another cable to maintain radio operation. So first we select the old substation node. Then we get the shortest path from the connection point to the old substation. And along this path, we want to open one cable. And I'm looking if we can get a visualization of this. Yeah, restart. Oh yeah, that's. Yeah, I'll go to the visualization then, because then it will be clear what we did. Let's see. Restart. Oh, it actually worked. Oppa, okay. So, right. So I moved this a little bit so we can see the connection that was made. So if we take a look, so previously the route with node 17 was congested, right? Now we have created a new cable from the substation. So that's this yellow cable, but just right now when we were doing the exercise, this cable was inactive. Using the optimization, we have determined that it's best, or it resolves the congestion if we open this existing cable and then we close this cable. And this actually makes sense also if we take a look at it, right? Now we divide this route into two parts. 17, 18, and 19 form the first part, and then 20 and 21 form the second part. And the second part is now supplied by the new substation. We did the same thing for the route containing node 1, except that this route is completely taken over now by the new substation, because we have determined that 1 is the closest node to connect the new substation to, and then it makes sense to close this feeder. That's the result of this assignment. Are there any questions?
Maybe a little bit of a noob question, but in this result, should the line between 20 and 21 now not be reversed? Or is it just, am I misreading the model?
Yes. I think currently this is a result of our visualizer. Cables don't have a direction, luckily. So I think it's just part of the visualization.
I
think it would be neater to reverse it, but for the load flow calculation, it actually doesn't matter. So, but I think you could say you're right.
It's topological direction, not flow direction.
Yeah.
Yeah, exactly. Power can flow both ways. I think that's the main gist.
So you're talking about the optimization function.
Yeah.
I would like to know what is the objective of this optimization function. So, for example, if there are multiple options to heal the congestion, then what exactly would that be? And second question is, you have considered the substation, but is it possible to simply use topological, so using the switches in order to do this optimization, or it's only about the substation?
Yeah, so I want to address the second point first. It's indeed valid that you could reconfigure the network in such a way that maybe the congestion would also be relieved. And so that's just another way of solving the problem. For now, we have decided to build a new substation. Then the first part of your question, what's the objective for optimizing this method? It's simply if there's no congestions available. So you could also formulate it differently. For example, when cables are least being used, in a sense, like if the least part of their capacity is used, that's another way of formulating the optimization problem. Does that answer your question?
Partly, because one aspect is not clear. Yeah.
Thanks. Due to time constraints, I'm going to cut off the discussion, but I invite you to continue it during lunch.
Sure, yeah.
Thanks for the nice interactive session. I hope you all enjoyed it. We're going for lunch now, and it's in a different building. That's why we're a bit short on time, so we really have to go now. We're going to lock off the room, so you can leave your stuff here. No need to bring it to the other building. And then, you can follow us. We'll walk as a big group to the lunch location.